So last time we ended with an introduction to white dwarf stars. Now, white dwarf star and a planetary nebula are both a category of objects that we call stellar remnants. So they're what left over after a star dies. So the planetary nebula, expanding cloud of gas. They used to be the outer parts of a star like the sun. The white dwarf is what's left from of the core of a star that used to be like the sun, and so that's that. These are stellar remnants. There are other kind of stellar remnants that are out there that result from how different kinds of stars die. More massive stars can die, and they can leave behind a neutron star or a black hole, and we'll be talking about those later. But a white dwarf star, when a star like the sun dies, you get a and so this is a diagram of the evolutionary tracks of stars, and so it leaves the main sequence, becomes a red giant, helium flash, horizontal branch star, starts fusing helium in a shell, also becomes an asymptotic red giant, and then expels the planetary nebula, and the core becomes a white dwarf. And so on the main sequence, you're fusing hydrogen to helium. As a subgiant, you're not fusing anything. As a red giant, you're fusing hydrogen to helium in a shell surrounding a core that's not fusing anything. As an asymptotic branch star, then you're fusing helium into carbon in the core, and there's a shell surrounding the core that's fusing hydrogen to helium. And then as an asymptotic, so this is a horizontal branch, as an asymptotic branch star, then you are fusing hydrogen into helium in a shell that's surrounding another shell that's fusing helium into carbon, which is surrounding a core that's not fusing anything. When you're fusing the helium into carbon, there's a little bit, that carbon occasionally grabs an extra helium and fuses into oxygen, so there's a little bit of oxygen produced in the process. Okay, white dwarf, nothing is fusing. You have a dead core, what's left of a core of a star that's mostly carbon and some. Very first white dwarf was actually discovered by William Herschel. He didn't know what he found. He just noted that the star 40 Eridani was actually a triple star system. And so we have the main star, which is a K-type main sequence star, has a companion star that's a white dwarf star, and there's another star there that's a red dwarf. The spectrum of all these stars was first measured by Walter Adams, in which he was surprised that the dim star there was much hotter than the primary star. Normally that would have made it much, much brighter, but it wasn't. It was actually dimmer, indicating that it was a tiny little thing. So, ironically, the next white dwarf to be discovered was by Alvin Clark, American optician, who built lots of telescopes. He was looking at the star Sirius, and he noticed that Sirius had a companion, tiny little companion. Now, both of these stars are measured to be spectral type A. Walter Adams measured it to be spectral type A about the year after he measured the other one. And again, it's tiny in size, because it is, even though it's spectral type A, it is very dim compared to the primary star, which is just a regular main sequence star. And so it was after this that they started using the term white dwarf to apply to these tiny little white stars that are much, much smaller. Seeing Sirius B is tough most of the time because Sirius A is so bright. And so what happens is that they're in elliptical orbits, and so some years they're actually fairly close together and you can't see them, and other years they're very far apart. So back in the late 1990s, they were so close together that you couldn't actually see them because they were so close together. Getting around 2015 to about now, 2020, they're about as far apart as they're going to get. And so this is really the optimal time if you get a good telescope to actually see that little companion, which is barely visible right there. Sirius itself, dog star. We talked about it in class. You go out at night, look at Orion. It's down to the left, brightest star in the sky. They orbit each other in a period of about 50 years, average distance of 20 AU, though sometimes much closer, sometimes much farther apart. We think that white dwarf is really only about 230 million years old. We think that what happened was that back when the dinosaurs were lived, this was a binary star and two really bright stars. And then one of these stars, a B-type star, died and left behind a white dwarf, and so it's comparatively young. So what happens to the white dwarf? Generally nothing. It just sits there. It's not fusing anything. It's not doing anything else. It just is gradually cooling off. Eventually they call it a black dwarf after it's completely cooled off. None of them have cooled off that point. In fact, the fact that we can't find any black dwarfs indicates that the universe isn't old enough for that to happen. In fact, this is one of the ways of estimating how old the universe is. We say that the universe has to be older than the oldest stars, and so we know about how long stars like the sun live. And so we know once they're dead, they become a white dwarf, and white dwarf does nothing except gradually cool off. And so we find the coolest white dwarf, and that gives us an estimate of the age of the universe, because we know the universe has to be older than that. And so we figure out how long it would take a star like the sun to live and then die and then become a white dwarf, and then how long it would take the white dwarf to cool off to the point that we see it. Well, it's mostly carbon. Dwarfs, as they cool off, they stay roughly about the size of the Earth, except they're mostly carbon, cooler and cooler and cooler. The sun, if you draw the sun as a current size compared to how big it is as a red giant compared to how big it is as a white dwarf. So over time, the sun continues to live as a main sequence star. It changes very little as a main sequence star. It gradually expands, becomes a white dwarf, and so forth. All the living and dying happens in a very short period of time. All the dying does compared to the life. It spends almost entire life as a main sequence star. That's why there's so many stars that are main sequence stars, is that they spend such little time off the main sequence that you don't see them. Now, you have this white dwarf. It's carbon. It's gradually cooling off, and eventually it will crystallize. Well, what's a crystalline carbon? Diamond. So imagine an Earth-sized diamond. In fact, we found a white dwarf that's cooled off to the point it's starting to crystallize. So it's turning into an Earth-sized diamond. And so this is the designation of that object right there. Okay. So it's roughly like a 10 to the 34 carat diamond. I imagine De Beers is already in the process of building a spacecraft to go mine it. White dwarfs are interesting. They're not ideal gas. Remember the degenerate electron system. So the more mass they have, the more energy they have, and the more they shrink. It turns out there's a maximum mass that a white dwarf has. The radius is roughly 1 divided by mass to the 1/3 power, up to a point. And that point is real close to the maximum mass it can be. Indian astronomer Chandrasekhar calculated the maximum mass of a white dwarf is about 1.4 solar masses. If it's bigger than that, it has so much gravitational energy that it shrinks and compacts itself down. It's no longer a white dwarf. It's all squeezed down to basically one big giant atomic nucleus. We'll talk about that. So Chandrasekhar figured out the 1.4 solar masses is the biggest it can be, And so we call 1.4 solar masses the Chandrasekhar limit, the biggest mass that a white dwarf can be, or any kind of degenerate electron system. So the more mass it has, the more it shrinks until it reaches 1.4 solar mass, and it shrinks down to one big giant atomic nucleus. Now, that doesn't mean the star itself cannot be bigger than 1.4 solar masses. It means the white dwarf can't be. Remember that stars lose a lot of their mass as a red giant. So even stars that are 1.5 or 3 solar masses, they will still become a white dwarf because they'll lose so much mass. In fact, we figure that a star can be up to 8 solar masses and still end up as a white dwarf because it's going to lose so much mass. So stars that are less than 0.08 solar masses, they never even become a star. They start off failed. They become a brown dwarf. Stars bigger than that, up to about 0.4 solar masses, they live their lives as a red dwarf star. None of them have ever died, but they will probably die as a burnt out sort of thing, similar to a brown dwarf, except all helium instead of a hydrogen mixture. Then what's going to happen, though, is 0.4 solar mass stars, all the way up to 8 solar masses, will swell up, become a giant, even a bigger giant. The bigger giant, sometimes called a supergiant, blow its outer layers off into space, become planetary nebula, and a white. So the question is, what about binary stars? Because they're going to behave differently because now you have another star that's in the way. And so that'll be our next topic.